morning everyone. Today we are going to have a paper on fundamentals of radioactivity. I am Dr. Pankaj Tandon from Atomic Energy Regulatory Board, Mumbai. The objective of this particular paper is to understand what are the concepts on stability of a nucleus in terms of neutron and proton ratio, to understand the radioactive law, different type of particles, units of radioactivity, to know the concept of half-life, different type of emissions during radioactive decay, to understand the effect of radiation on human health. My presentation on this particular topic outlines the four important things. First is introduction to radioactivity, sources of radionuclides, background radiation, application of radioactivity. This is one of the important symbols which you might have come across at many places, which talks about there is radiation in hospitals, in industries. This place shows that there is a radiation at that particular point. Now, we should know what is radioactivity, how radioactivity is defined. If you see the literature, nuclear decay or radioactivity is the process by which a nucleus of an unstable atom loses energy by emitting ionizing radiation. A material that spontaneously emits this kind of radiation, which includes the emission of alpha particles, beta particles, gamma rays and conversion electron. So, this tells what is radioactivity. We all know these two important laureates. First is Anthony Henry Becquerel and Marie Curie. Because of this, only there is a term radioactivity defined, and now today in the world we are using radiation for many useful purposes. The important question which comes to our mind: why are elements radioactive? Why we say this element is radioactive and this not? We all know there are unstable nucleus. Unstable nucleus means they have excess energy, and when they have an excess energy, as a law of nature, everything wants to go to the ground state. So, this unstable nucleus which is having excess energy, they would like to come to a ground state, and thus when it comes to ground state, they emit different kind of radiations. The radiation which is being emitted while coming from unstable state to a ground state are ionizing radiations. This is very important pictorial picture or pictorial graph which tells about the radio waves, microwaves, infrared, visible, ultraviolet, X-rays and gamma rays. If you see this particular picture, we can find out the wavelength decreases from radio to gamma, and in the way the wavelength decreases, the frequency increases, because wavelength and frequency is inversely proportional. It shows below that there is a building which talks about radio, and there is an atomic nucleus which talks about gamma rays. This is called an electromagnetic spectrum. Now, we should know what are the sources of radioactivity. As we understand, there are three different sources of radioactivity. First is called primordial radionuclides. That radionuclides that are present since the creation of Earth and having a half-life much longer. Talked about lead, radium, potassium. We have potassium in our body also. Now, similarly, there are second kind of radioactivity is or defined as cosmogenic radionuclides. That radionuclides that are produced in the upper atmosphere as a result of cosmic rays, interaction with light particles like carbon atom and oxygen, and we get different radionuclide like carbon-14, beryllium, sodium, phosphorus and sulfur. These are all radioactive material. Now comes the last in which this category is defined is called anthropogenic radionuclide. That radionuclide that are produced as a result of man-made activities such as nuclear fuel fabrication, enrichment, nuclear power generation, nuclear accidents, etc. And you know, whenever such incidents takes place, we got a radioactive material like cesium-137, cesium-134, iodine and strontium. It means we have defined radioactivity in three different forms or three different parameters: primordial, cosmogenic and anthropogenic. Now, if you see this particular picture, it talks about the sources from where it emits. It goes to the atmosphere, then comes to the man or animals, then comes to the plant, and plant it goes to soil. From soil it may again go to plants and plants to man. What does it mean? What is natural background radiation? The natural radiation energy between few kilo electron volt to mega electron volt from primordial radionuclide are called background radiations. As we defined in the previous slide, what is primordial background radiation? The radiation which is coming from in the range of kilo electron volt to mega electron volt, and these are background radiations, and they may be in a terrestrial or extraterrestrial origin. So, this particular picture tells about the source. It goes to the atmosphere or it may come to the soil. When it goes to the atmosphere, it may come to the man or animal. From man and animal, it may come to the plants, and if you see the reverse cycle, from plants it may be taken up by man or animals. Similarly, when it comes to the soil, from soil it goes to the plants, or if it comes to the plant because of man and animals excreta, it goes to the soil. So, these are what it is called background radiation. Now, artificial radionuclides. We all know, we have read in the literatures, in our books, there are two different kind of radionuclides. One is artificial, one is man-made. Over the last few decades, man has artificially produced hundreds of radionuclides for various purposes in medical, for industry, for research, for agriculture, and these artificial radioisotopes to the atmosphere during the course of operation of nuclear fuel cycle, nuclear test and nuclear accidents. Most of the artificial radioisotope decay having short half-lives. Therefore, only few of them are significant from the point of human exposure. What do you mean by short half-life and long half-life? That we are going to discuss in next few slides. The question comes, artificial radionuclides, when we are making it or producing it, there may be some advantages for that. First of all, when we are dealing this particular module, there are certain key definitions which we should also know. Until unless we will not be able to understand the radioactivity. Few terms which comes when we define the word radioactivity is Z. Z is nothing but atomic number. It is the number of protons in the nucleus of an atom. Nucleus, what is nucleus? It is nothing but a proton and neutrons which are located in a form in an atom is called nucleus. Now comes proton. Positively charged particle in the nucleus of atom is called protons, and mass is nothing but 1 AMU. What is neutron? Neutron are the particle which are neutrally charged. It means they do not have any charge. As we define the proton a positively charged, electron the negative charge, neutrons do not have charge, but neutron and proton both combine to make a nucleus. Then comes mass number of an atom. Number of protons and number of neutrons in the nucleus is called mass number. Now it means we have defined what is atomic number, what is proton mass number, and what are different type of particles like proton, neutron, electron, and proton, neutron both combine to make a nucleus. Now see this particular picture, how beautifully defined the radioactive decay whenever the decay takes place. Why the decay takes place? Because atoms which are unstable, they want to come to a stable state. How they can come to the stable state? We should know the neutron by proton ratio. If there is a neutron per proton ratio is not same, it is much higher, it is going to decay to become stable. This particular picture talks about alpha decay, beta decay, gamma decay and neutron. Now there are three common types of radioactive emissions. One is alpha, one is beta, one is gamma, and they are all prominent in nature. We all come across in day-to-day work three different kind of radiations emission like alpha decay, beta decay and gamma decay. What is alpha decay? How to define alpha decay? You have seen the americium-241 isotope. When it decays to neptunium-237, how when it decays, it comes out an alpha particle. What is the alpha particle? That will come across the next slide. Then there is decay called beta decay. When tritium comes to helium-3, there is a decay called beta decay. It clearly shows when the beta decay is taking place, electron is coming out. Similarly, gamma decay. Gamma decay is nothing but when an isotope comes to the other state of an isotope, there are some excess energies there in the nucleus which comes out in the form of some radiation, and they are called photons. It means we have three different kind of decay, alpha, beta and gamma, and most of the radioisotope decay by this particular mode. Since last few slides we are talking about a nuclear stability. What is nuclear stability? There is a neutron by proton ratio. What is neutron by proton? It means the nucleus, there are neutrons, there are protons. If neutron by proton ratio is 1, it means the isotope is stable. But when there is a change in the neutron by proton ratio, then it means the nucleus is unstable. And so what happens? Either neutron convert to proton or proton converts to neutron. So there kind of reaction and unstable nucleus comes to a stable. This is a belt, a graph we all see whenever we talk about radioactivity in books. Is a nuclear stability belt. Now, in the few slides back, we were talked about the kinds of radioactivity. Summary of radioactive decay, if we talk about alpha, beta, gamma. But apart from that, there are two different kind of emissions called positron emissions and electron capture. When we talk about alpha particle, as I was discussing, there is a decay. Particle emitted is helium nuclei. What happens when a helium nuclei comes about? What happens to the mass number? The mass number decreases by 4 and atomic number by 2. When beta decay takes place, what happens? When a beta particle emits, there is no change in the mass number, but atomic number increases by 1. When gamma emission takes place, again no change in the mass number, no change in the number of the atomic number, but there is emission of energy, and that energy is called photons and which is called gamma emission. We come across positron emission and electron capture. There are two different kind of emissions. In case of positron emission, particle emitted are positron. What happens to the mass number? No change. What happens to the atomic number? Decreases by 1. When we talk about electron capture whenever takes place, it means there is a vacancy in the orbits. When electron capture takes place from K shell by nucleus or from L shell to K shell, then what happens? There is a change in the energy. The vacancy is created, and because of the vacancy, the photon is coming out, energy is coming out. If it is coming out from K shell, it is called K, otherwise it is called X-ray photons. And there is no change in the mass number or atomic number. Yes, atomic number again decreases by 1. It means when a positron emission takes place or electron capture takes place, both have same kind of effect, that atomic number changes by 1. Now, there are three different isotopes. What is isotopes? They are the atom of same element that have different number of neutrons. If the neutron changes, it means electron and proton, like we talk about three different isotopes of hydrogen. One is protium, second is deuterium, and third is tritium. It means one proton. In case of deuterium there is one proton and one neutron, and we talk about tritium, there is one proton and two neutrons. So there are three different isotopes or radioisotopes of hydrogen, because there is change in the proton in all the three. Protons are same, but neutron there is a change. Now we have dealt in the previous slides about different kind of radiation, but we should know now what are the unit of radioactivity. Becquerel is the unit of radioactivity and is defined as disintegration per second. What is Curie? 1 Curie is nothing but 37 or 10 to 9 becquerels. So 1 millicurie is nothing but 37 megabecquerel. It means 37 into 10 to 6 becquerel. When we talk about 1 microcurie, it is nothing but 37 kilobecquerel. The second important unit is RAM, Röntgen equivalent man. RAM is usually a term used to describe the equivalent or effective radiation dose. In the internal system of unit like SI units, sieverts is the unit of dose, which is nothing but describes an equivalent effective radiation dose, and usually defined at 1 sievert is nothing but 100 rams, or 1 grays 100 rads. Now comes to the important term radioactive half-life. What is radioactive half-life? Usually all radioactive elements, they decay, as we are discussing in the previous slides, and when they decay, they comes to the second state or ground state or other isotope form. The half-life of an element is the time that it takes for half of the material you started with to decay. It means you started with X, after some time when it becomes X by 2, it means the half-life is, it defines the half-life. It does not matter how much you start with. After one half-life, half of it will have decayed, half of its original quantity. Each element decays into a new element, like carbon 14 decays into nitrogen 14, while uranium 238 radioactive decays into lead 206. Half-life of each element is constant. It is like a clock keeping perfect time. Whatever in the physical or chemical form the radioisotope is there, half-life never changes. Half-life is always the life in which half the radionuclide decays from its original value, and that remains constant. This particular picture, if you see, radioactive half-life. Half-life starts from uranium-238 and how it is coming to lead-206. Various decays are taking place from alpha, beta, then there is certain change of energies, and now the way it comes from how many years, 10⁵ years to 10⁻, and finally it comes to lead-206. This is how typically we define the radioactive half-life. Now when we see this particular picture, how much of this element remains after 4 half-lives? As we define, 1 half-life means half of its element is remaining. Now one more half-life goes, 2 half-life means again half. The third, again half. It means when we started with 100%, the first half-life it goes 50%, second half 25%, third life 12.5, and similarly it goes 6.25%. In this way the half-life is defined. Half-life may be in years, maybe in days, maybe in seconds, maybe in minutes. Now there are different types as we talk about alpha, beta particle and gamma. This particular picture, if you see, it clearly shows about whenever alpha particle comes out, the 2 neutron and 2 proton comes. Beta particle, either electron or a positron, and gamma is nothing but photons. It is always called X-rays, gamma rays. This particular picture clearly tells about Okay, what are the different kind of materials are required to shield this particular radiation? Like alpha, a paper is good enough. For beta, even hands or skin can good enough. But for gammas and X-rays, we require a concrete. It's a beautiful picture about radiation penetrating power. The race starts between alpha, beta, gamma. Alpha, paper can be stopped. Beta can be stopped by glass. Finally, who is winning the race is nothing but gamma, who has crossed paper, able to cross glass, and finally lead. If the lead is not equivalent thickness, the thickness of lead is not proper, the gamma comes out and see, it talks about I win the race. Again, similarly, we have again defined the pictorial graph of alpha, beta, gamma. Alpha particles may be completely stopped by sheet of paper, beta particle by aluminum shielding, and gamma rays, however, can only be reduced by much more substantial objects such as a very thick piece of lead or concrete. Is radioactivity gives health problem? We talked about alpha, beta, gamma. They are all ionizing radiation. What do you mean by ionizing radiation? It is going to do the ionizing of the matter. It means when it comes and interacts with the body, definitely some reaction takes place, some effects takes place. And alpha, beta and gamma particle all add energy to the body tissues. The effect is called ionizing energy. It can alter DNA. Even though alpha particle is not very penetrative, if the decaying atom is already in the body, like inhalation, but they can cause trouble. It means when the radioactive material is outside the body, you are going to give an hazard. But when it goes inside the body, because of inhalation and ingestion, it is going to decay and it is going to harm. Alpha, beta is going to harm, but gamma may come out. The important three principles, which are called cardinal principle, by which we can able to shield the material or shield this particular radiation, is by time, distance and shielding. These are three principles which talks about that you can able to protect yourself. If at all you are going to be with minimal time with the radioactive material, then you are going to be less exposed. If you are going to handle radioactive material large distance, then again exposure is less. And if we use some kind of shielding material, as we discussed about paper, aluminum, glass for beta particle like, or concrete or lead, you can able to protect yourself. Now this particular slide, if you see, there is an X-ray machine. What is happening? It is giving some kind of radiation. You are able to get the picture of the chest X-rays, a film, and finally you come out. The person who is coming out is not a radioactive person. He doesn't have any radiation, but he has been exposed and got the film. Dose or radiation dose is a generic term for measure radiation exposure. In radiation protection, dose is expressed in milliramps. We talked about the quantity RAM. Now, when we are using a solid material, solid radioactive material, or a radiation generating equipment like X-rays and all, we are going to get exposed. But the situation changes when the material is in the form of liquid, because while handling liquid radioactive material, there are chances of contamination. But contamination is what? It is the presence of radioactive matter in any place where it is not desired, and especially in any place where its presence could be harmful. So if there is a spillage and which can lead to some kind of harm, it is called contamination. Now this particular slide talks about the medical application. As we told, when we talk about radiation or radioactive material, it is having certain parameters or certain applications. Radioisotopes with short half-lives are used in nuclear medicine because they have the same chemistry in the body as a non-radioactive atom. In the organs of body, they give off radiation that exposes a scan giving an image of an organ. It means suppose you would like to take a thyroid scan, would like to know how the thyroid is functioning. You give a radioactive material, it starts emitting some kind of radiation, it is to be detected with a detector and a scan is produced. It is nothing but a thyroid scan, which tells your doctor whether your thyroid is functioning normal or abnormal. Now comes to the application of radiation in industry, leak detection. This use of radionuclide tracer to find the leaks of flow path has wide application. Industry. Finding the location of leaks in oil well castings, determining the tightness of abundant slate coils for the temporary storage of oil, looking the position of leaks in refrigeration coils, finding leaks in heat exchanger piping, locating leaks in engine seals. It means the places with the flow of liquid. If you want to know any leakage has taken place, radioactive material plays a very important role. This slide text talks about when there is a flow of liquid and we would like to know how much, at which particular point there is a leakage. Then what happens? You just, with the liquid, you give some kind of radioactive material as a tracer. When the tracer flows, some radiation is being emitted, and the place where you find that the holes are there or some leaks have taken place because of joints crack and all, you find the counts change, there is a change in the count. So, this is the way to find any leakage in case of lines where the liquid have been flowed, where you cannot able to open and find out. If you want to control the thickness, we all know papers have been produced. The manufacture of aluminum foil, if you want to see it, the aluminum foil manufacturing is going on, but we have to maintain the thickness of this particular foil which is being produced. How it can be done? Beta emitter is placed, beta is emitting, radiation is coming out, detector is there, and finally we have a computer. This computer tells about by a system if there is any change in the thickness, and finally it feeds to the roller, and roller then maintains the thickness. Now this is very important thing. We always know carbon dating. When a living tissue is there is a carbon 14 by carbon 12, there is a ratio which is same as atmospheric ratio. If the change is taken place, you can able to find out, yeah, change has taken place, and with that possible dead tissues. Now this mummy you can find out which is frozen in the Italian Alps. Now if I would like to know how old it is, by using carbon dating we can able to find out, and this particular mummy is 1991, it was found out, and we can able to find how old it is, at least 5000 years old. The importance of radionuclides, as we have seen in case of agriculture, we can able to do the improvement of the crops by mutation techniques. The crops which gets we can say which the life of the crop, you can increase the life of the crop by using this particular radiation. As you can able to see that when the radiation comes on the seeds, then the mutant cultivars and how it takes place, and when there are no negative mutations and when there is no mutation, how it changes. Insect pest control. You can see this radiation which is very useful in case of agriculture where the insects are there. How to really control this particular insects. It can be used as a pest control, and you will full particular type of this you can able to control this particular insect which is going to create a problem for our crops. Preservation of food and agriculture product by radiations. You might have come across different kind of potatoes, onions and different type of spices where we increase the shelf life by using radiation. This is one of the alternate method of food preservation by irradiation of X-rays and gamma rays. It is used to prolong the shelf half-life of many food and agriculture products. It destroys bacteria and microorganisms in food, pre-packed or bulk and grains. The food exposed to controlled amount of ionizing radiation in shielded area for specific time to achieve desirable objectives. So what does it mean? It means we are trying to increase the shelf half-life of the food by exposing different kind of radiations. The sources are gamma rays from cobalt-60 or cesium-137, X-rays up to 5 electron volt, electron accelerators also being used up to 10 mega electron volt to preserve the food and agriculture product. See how the food has been preserved. by giving the dose from 0.05 kilogray to 0.15 kilogray. It means the onion and potatoes we can preserve by using different kind of radiations. Now see radioactive consumer products. We all know smoke detectors, their watches were there. What happens? They have radioactivity and it shines. Very small amount of radioactive materials are being used in these products which are called consumer products, which does not have any kind of harms, but it is very useful for our day-to-day work. Dentures, initially in dentures also it has been used. This particular thing is very well given in the literatures, that very small amount, less amount of concentration of quite low, it has been used, but now we have stopped because of the harmful effects. It means to say that there are the uses in every application. Radiations are there many places, but some of the places we have to stop, like dial painting, in dentures, etc. Now this particular slide tells about the sources of background radiation as of now. Radon, if you see the cosmic rays, it gives 8%. Terrestrial rays gives 8%. There are certain man-made radiation sources which are being used for medical X-rays like nuclear medicines, radiotherapy, consumer products, and how this particular background radiation, if you compare, it means in the background radiation is also radiation which is being used, which has been there, which you cannot reduce it. But during applications, if we can able to use the radioisotopes in a proper application in a way that it should not give any kind of harms like nuclear medicines or consumer products, then it is very useful for the peaceful purpose in human mankind. So in summary, we would like to say that radiation is energy given of a matter in form of rays or high speed particles. All matter is composed of atoms. Atoms are made of various parts, like nucleus contains minute particles called protons and neutrons, and the atom's outer shell contains other particles called electron. Nucleus carries a positive electrical charge while electron carries a negative electrical charge. These forces within the atom work towards a strong stable balance by getting rid of excess atomic energy, and that is called radioactivity. So we have seen how radioactivity is very useful. What is radioactivity? What are different type of radiations are being coming out? What are the harmful and useful effects of radiation? In that process, unstable nuclei may emit a quantity of energy, and this spontaneous emission is what we call radiation, and the process is called radioactivity. This particular topic is very useful for human mankind if the radiation which is being emitted by radioactive material is used for peaceful purposes. Thank you very much.